of Computer Science at NIT Raipur. I warm welcome. Just a minute. I warm welcome to all the session chairs, Dr. Saroj Kumar Viswas from NIT Silchar, Dr. Krishna Kumar from NIT Uttarakhand, and Dr. Alok Kumar Singh Kushwaha from Central University, Guru Ghasidas University, Bilaspur. I also extend my warm welcome to all the paper presenters of paper ID 185, 303, 319, 362, and 474. And I would like to introduce today's session on machine learning methods in computer vision. That is session 3 under the track 5 for computer vision. Now I would like to request Mr. Surendra to, can you please introduce more about our session chairs to our participants?
Yes, ma'am. Thank you, ma'am. A very good morning to all of you. On behalf of Department of Computer Science and Engineering, NIT Raipur, and the 4th International Conference on Machine Intelligence and Signal Processing, I welcome all the respected session chairs and participants. Before we start the session, let me introduce our esteemed session chairs. Our first session chair is Dr. Saroj Kumar Biswas. Dr. Saroj Kumar Biswas is currently Head of Computer Science and Engineering Department at NIT Silchar. His research interests include machine learning, artificial intelligence, pattern recognition, data mining, deep learning, and image processing. He has published more than 90 research papers, including 26 unpaid SCI index journals in various reputed publication houses worldwide, including Elsewhere, IET, Springer, Wiley, Taylor and Francis, World Scientific. Our next session chair is Dr. Krishna Kumar. Dr. Krishna Kumar is Assistant Professor and Head in CSE Department, NIT Uttarakhand. He received PhD and MTech in Department of Computer Science and Engineering from Visvesvaraya National Institute of Technology, Nagpur, India in March 2019 and MTech in 2014 respectively. He received BTech degree in CSE from Government Engineering College, Paniwala Mota, Sirsa, India in May 2011. He is authored or co-authored more than 75 technical research papers in top-tier international conferences and journals. His research interests include multimedia security, video processing, machine learning, deep learning, real-time systems, virtualization, cloud security, cyber security, natural language processing, and recommender systems. Our next session chair is Alok Kumar Singh Kushwaha. Alok Kumar Singh Kushwaha is affiliated to Department of Computer Science and Engineering, Guru Ghasidas University, a Central University, Bilaspur, where Dr. Alok Kumar Singh Kushwaha is currently working as Associate Professor and Head of Department. Alok has more than 13 years teaching experience in different reputed universities. He earned his PhD from Indian Institute of Technology, BHU, Varanasi. Dr. Alok has published more than 70 publications in reputed journals and conferences. Dr. Alok Kumar Singh Kushwaha major research interests include deep learning, machine learning, computer vision, and artificial intelligence. Thank you, sir. Thank you, sirs. Thank you all the session chairs for joining. So in this session, we have 5 papers to be presented. May I request all the session chairs and participants to turn on their video. So that we will be taking a snapshot. Can you please turn on the video, all the session chairs and participants? Okay, thank you. And may I request the session chairs to start the session?
Yeah, you can start.
Yes, proceed.
Yeah, you can start.
I think
Now-
we can start with
Hi.
paper ID 185.
And actually, there is one small change. Paper 471 requested for the first slot.
Can you
So,
please repeat, Devendra?
paper ID 474 has
Okay.
requested for the first slot, ma'am. So,
Okay, okay, okay.
yes,
Okay. And I
So,
request all the paper presenters, please stick with the time. You have 10 minutes for presentation and 2 minutes for question answer.
okay, paper ID 474 can present. You can present the screen. Sandeep Kumar Sharma.
Hello.
Dr. Sandeep Kumar Sharma, are you available?
Yes, sir. Audible, sir.
You can please present the
Can I
screen.
start, sir?
Please present your screen. Your PPT is not visible.
Okay, sir. I'm going to start, sir. So is the screen
Yes,
visible,
now,
sir?
yes, it is visible. Please go to your PPT.
Okay, sir. I'm going to start my PPT.
Okay. You can please full screen it. Slideshow. Yes. Okay, you can start.
Okay. Good afternoon. One and all present here. This is Sandeep Kumar Sharma. And here I'm going to present my research work titled Digital Image Transformation Using Microfertility Cellular Automata.
And sharing option.
So in this presentation, I would like to cover these contents. So first, overall, I would like to explain the introduction about the research. So this is digital image processing uses various algorithms to process different type of digital images, and in these algorithms, number of useful information was extracted by these algorithms. So again, digital image processing has many advantages as compared to analog image processing. And wide range of algorithms can be applied to input data, which can avoid problems such as noise, signal distortion during processing. Objective of my research is the objective of the proposed research is to provide unique methods which are used for image transformation.
Excuse me,
The methods
Sandeep Kumar.
are could be used as an intermediate function to implement image-based applications such as
Mr. Sandeep,
age detection, pattern recognition, object identification.
you are audible.
And yes, ma'am.
Actually, some background noise is coming. Can you please your headphone or any?
From actually, ma'am, from my side there is no issue there. Maybe someone audio is open.
Okay, okay. So I request all other participants, please mute your mic. Thank you. Go. Please continue, Mr. Sandeep. Please continue.
Okay, thank you, ma'am. So here in the research, I would like to discuss three methods which was implemented by me. These are the luminosity function, vitality function, and threshold frequency function. So literature review. The images are transformed using various classical techniques. Actually, for image transformation, various methods are available. And some methods are based on gradient technology and some are based on Laplacian technology. Basically, the gradient-based technologies process the image by taking minimum and maximum first derivation of the image. And basically, the Robert, Sowell, Prewitt, and Kenny methods are using the gradient technology. And the Laplacian-based techniques transform the images by applying second-order derivation. And the second-order derivation approach works by searching zero crossing. The Laplacian derivation calculates the shape of each pixel for highlighting location of the pixels, and Marsh-Hildreth method is based on the Laplacian approach. So what are the gaps in the existing research and what are the disadvantages we can say? So basically the classical operators perform image transformation by selecting a convolution operator, or we can say a kernel. And if the kernel size, or we can say the convolution operator size, is small, then in that case the transformed image may suffer from the noise. And one of the very powerful method, that is Kenny. Kenny also having some drawbacks, like the Kenny method consume very much time as compared to other methods. So these are the some drawbacks with the existing methods, and I have tried to cover these gaps in my research. So why I have selected this research? So motivation behind the research. So as we know that image processing has a wide range of applications, and lot of applications exist in the society, like automatic vehicle driving, robotics, pattern recognition, and medical science also use the image processing. And so due to these wide range of applications, I was motivated to select image processing. And there are a lot of gaps in the existing research. That's why I have selected this area as a research. In my research, I have used a technology whose name is cellular automata. So basically the cellular automata is automata-based technology which read the value of a cell as a current state and apply a transition function, or we can say rule, and that generate a new state. Basically different types of transition function we can define with the help of to analyze the nearby cells, and these transition functions are called like 4 cell, 5 cell, 8 cell, 9 cell, and 25 cell. 4 cell means if we consider only left, right, and up and down cells, and 5 cells if we include the centered cell also, the cell which are going to transform, and 8 cell in which we are including the outer cells, and in 9 cell we include all the outer cells including the cell itself, and in the 25 cell thresholding method we
Sandeep, go to your methodology.
Yes, sir.
Propose methodology.
Okay, so here I have implemented 3 methods. So first method, that is luminosity method. So basically this luminosity method convert the image into grayscale image by extracting the color components. So in this way the color components are abstracted and apply the equation, and with the help of this equation we can convert the image into grayscale image. And this is a vitality function. Basically this function is used to enhance the quality of image. So basically this method smooth the image by removing the blur or noise. So to implement this method, we have to divide the image into squared size of regions like 3 by 3 or 2 by 2. And then we have to add some virtual rows and columns to the selected region. And after that, we apply the method to enhance the image. And this one I would like to explain with the help of example.
Sir,
So here,
hello, excuse me. Can you please speed up, sir? Actually, 10 minutes has already passed.
okay, sir. So here the source region I have selected from the image, and here you see I have added a virtual rows and columns outside the region, and after that I have applied the average operator, and this operator is applied to the region, and after applying this operator, this is the output, and this is the more enhanced region as compared to the previous one. And the threshold frequency method, basically the threshold frequency method analyze the nearby cells and then find the threshold value, and with the help of this threshold value we can identify the targeted objective of the particular image. So here the equation TF4, TF5 is used to analyze the 4 cells, 5 cells like that, and these two equations represent the threshold value which are calculated by analyzing the 8 cells or 9 cells. So experimental results. So basically this method is implemented on number of images and compare with the existing methods also, and the criteria which are selected mean square error and peak signal noise ratio, and yes, of course time also. And here I have displayed the data as compared with the 5 images, and here you can see the MSC values are compared with the help of Sobel, Privet, Robert and Kenny methods, and the value of MSC is comparatively low as compared to the existing methods. So means that if the MSC value is low, so the transform image contain the very less noise. And these are table which represent the PSNR value. PSNR means which represent the similarity of the images. So here the PSNR value is higher as compared to the other methods. So means that the transform image is more similar to the source image. Okay, and now the summary and result discussion. So as we have discussed, the MSC value is low and the PSNR value of the proposed method is high. So we can say that the produced image may contain the very less amount of noise and having the high similarity with the source image. And conclusion, the cellular automata technology is able to process any type of images and efficiently enhance the quality of image and transform into different color spaces with negligible amount of noise. The proposed research is claimed that the produced threshold value could be used to efficiently implement image-based applications such that edge detection, object detection, and computer vision. Future scope. The future scope of the proposed research is to implement machine learning applications which are beneficial for the society. And these are the references which I have used during the research. Thank you. Is there any query you can ask?
Sir, any queries from the session chairs?
Sandeep.
Yes, ma'am.
Yeah, Sandeep.
Yes, sir.
In your method, just you have
Yes,
added
sir.
the
Yes, sir.
hello. You just combine the cells, means the pixels, to transform the image to new image, right?
Okay.
You combine the pixels, right?
Yes, sir. So actually, I have analysis the nearby pixels, and after that, the threshold frequency method is applied, and then the target pixel is decided.
So I could understand you have done experimentally the things. Do we have any philosophy and scientific justification behind that?
Scientific justification.
Yeah, how your method is means getting better result than other methods.
Sir, actually that this my method, this is automata based method, and this one automatically identifies the behavior of the nearby cells. And after identifying the behavior of the nearby cells, it try to provide the best result. Means that it may select the pixel whose quality is better, and then whatever the characteristics that that pixel have, accordingly decide what will be the new pixel, and accordingly it can enhance the quality of image. And yes, of course, this method is also used to implement some image based applications also, sir. So
you
basically
are transforming into grayscale, right?
Okay, sir. Yes, sir.
Just last question: how gray image and color image is different? How some noise is coming? I think.
Yes, sir. Actually, gray image
Yeah.
basically represented with the help of eight bits. And here only two components are there. Only two color components are there, black and white. And the gray color basically generate by mixing the white and black colors. And in the color image, like if RGB image is there, so here three components are there. And basically each component is represented with the help of 8 bits. So in gray image, basically 256 components are there, 2 to power 8. But in color image, a lot of color combinations are possible. Like 24 bits are there, so 2 to power 24. So such type of color combinations are possible in color image, basically in RGB image.
Okay, thank you.
Okay, thank you very much, sir.
Yeah, Sarma, I have one question that regarding your somewhere virtual region you have added on, how these values are going to be decided? Is there any like kind of concept padding? Am I audible? Hello?
Yes, sir, you're audible, sir.
Yeah, Sandeep?
Dr. Sandeep Kumar Sharma, are you available?
Hello.
Hello, Sandeep Kumar Sharma.
Hello.
Okay, maybe.
Yes.
He's present, I
He's
think,
present,
with the
but
participants, but
it's muted.
maybe some audio issue or any other.
Sandeep, please unmute yourself. Can you unmute yourself? I think you muted. Okay, so we may proceed.
Or if
Hello?
any other co-author present here,
Co-author is there?
then he or she can also reply the answer.
Hello.
Yeah, Anil is there? Okay, we without wasting time, we may proceed for the next one.
Yes, sir.
Please. So, yeah.
So next presentation, paper ID 185, Mr. Gaurav.
Hello, am I audible?
Yes, sir, you're audible. Yes, sir, screen is visible. You can start the presentation.
Okay, thank you, sir. Good afternoon, everyone. My name is Gaurav. I'm a PhD scholar from Manipal University, Jaipur. My guide name is Dr. Pratishtha Mathur, and she's also the co-author of this paper. My paper title is Empirical Study of Image Captioning Models using Various Deep Learning Encoders. These are the contents that I will discuss in this paper presentation: background, literature, survey, problem description, methodology, results, and conclusion. Basically, image captioning deals with the generation of some meaningful captions for the given image. It's a very important research topic in the field of computer vision and NLP, natural language processing. Basically, it does not only detect the important objects from the image, but it also identifies some important relationship between various objects so that a meaningful caption can be presented. There are some other earlier methods like template and retrieval based methods that have been implemented for the image captioning. But these methods had some limitations of missing out important objects. Like in case of template based methods, this method has some fixed size templates, and these templates has to be filled by the objects. But it is not necessary that all the important objects are covered and important properties are covered. So it may miss some important objects. Similarly, in case of retrieval based methods, some images are identified which are relevant to the query image. And using the captions of these images, one of the final caption is selected, and that is the final caption for the query image. Again, this method is useful, but again, it may miss some important objects. But because it is not necessary that the relevant images are containing all the objects that are present in the query image. So now recently, encoder and decoder based approach has been used by many researchers, and this approach has provided much better results. So in this paper, we have compared the performance of image captioning models with various image encoders. Like as I discussed that in image captioning, we use encoder and decoder. So I have compared various image encoders in this paper by using common decoder, and the decoder is GRU, that is gated recurrent unit. So I have used various encoders like VGG, Visual Geometry Group. There are two versions, VGG 16 and 19, residual networks, Inception V3, and the decoder I have used is GRU, gated recurrent unit. This is the general architecture of image captioning model by using encoder and decoder method. First, we have input image, and it is applied to the encoder. It retrieves the important features from the image, and then those features are passed to the decoder. A decoder uses the image features and generate the final caption for the given image. This is the basic architecture that is based on the encoder and decoder based framework. Basically, I have studied many papers that are image captioning based models. As I discussed earlier, methods are related to some template and retrieval that I've already discussed. That in case of template based methods, there are some fixed size template which are to be filled up by the image objects and their properties, but they may miss some important objects because it has to be a fixed size template. And in case of retrieval based approach, this was used in which some images were matched with a query image. Query image means the final image on the for which we have to generate the caption, and final caption used to generate using the captions of these related images. So there were some limitations, and recently approaches are based on encoder and decoder, and these are some papers that have used encoder and decoder. Actually, I have mentioned only few of the papers, but I have studied many papers that are based on encoder and decoder based frameworks. Some have used attention mechanism, some are simply using encoder and decoder, some are using multi-layer architecture from the decoder side. So various combinations have been used. So one of them is like deep hierarchical encoder decoder network, which uses deep networks representation power to efficiently combine vision and language. Vision means image features, and language part is second decoder part, language semantics. At a high level in the production of captions, there is a model that is used for domain specific image caption generator that uses a semantic ontology to deliver natural language descriptions for a given domain by combining object and attribute information with attention process to construct captions. There is one more model that emphasizes multitask learning, which helps to increase model generality and performance. As I discussed that I have only mentioned a few of the papers, but there are many models that have been implemented by the researchers using different approaches for the betterment of generation of caption. Now what I have done is basically in my paper I have compared the existing encoders to find out the best one which may generate better blue score. It is one of the evaluation metric or evaluation parameter. So I have used the encoders like VGG, residual network, Inception V3, while using GRU as a common decoder, gated recurrent unit as a common decoder in all the different models for the purpose of text generation. And how I have evaluated these models using the Flickr 8K dataset. I have implemented these models using Flickr 8K dataset, and the result I have evaluated on the basis of BLEU score, BLEU, bilingual evaluation understood the study. There are many evaluation parameters or evaluation metrics, but this is the most popular evaluation metric. So I have considered this one as one of the evaluation parameter for my paper.
Mr. Gaurav, can you please speed up?
Yes, sir. Okay. So this methodology I have used simply encoder and decoder based approach. In first model, I have used VGG 16 encoder, GRU decoder, and evaluation metrics BLEU 1, 2, 3, 4. In the coming slides, I have mentioned these. What are these like parameters 1, 2, 3, 4? In second model, I have taken VGG 19 as encoder, GRU decoder, and the same evaluation. Encoders will be different in every model. Decoder and evaluation metrics are same. Third, ResNet, and in fourth, Inception V3. So in this slide, you can see the result of the different models where VGG 16 in first model VGG 16 is the encoder, second model VGG 19 is the encoder, in third Inception V3, and fourth is the ResNet. And these are the evaluation parameters, BLEU 1, 2, 3, 4. Actually, here you can check the results of the different combination of model is present using BLEU scores. BLEU score refers the level of match between generated caption and the reference caption. Reference caption is from the text-based images. Like we have training part and testing part. So from the testing part, I've taken some images to evaluate the model. So reference caption is already given. Generated caption is the generated caption by the model, and these are the compared. And then we can obtain the BLEU score. So BLEU score comes between 0 and 1. When score is 0, it means there is no match between the generated caption and reference caption. And score 1 means there is a full match between the generated caption and reference caption. So BLEU 1, 2, 3, 4 score like 1 means only one word at a time is matched, and BLEU 2 words, a pair of 2 words are matched at a time. In 3 words are matched at a time, and 4 words are matched at a time, and the overall combination and then aggregated, and a final BLEU score is calculated. Here is a sample Python code. Just I have mentioned here to show that how BLEU score is calculated. This is the library, and this is the module, and these are the list, reference, and candidate. There may be more captions, but I've taken only one example. Reference caption, this is candidate caption, this is the function sentence BLEU. Then these are the parameters. Reference as first parameter, candidate is second parameter, weights like 1, 0, 0, 0. So here 1 as the first parameter, it will evaluate the BLEU 1 score. If I write like 0, 1, 0, 0, it will calculate BLEU 2. Like I write if 0, 0, 1, 0, BLEU 3, and 0, 0, 0, 1, it will calculate BLEU 4.
No need to discuss the code.
Okay, sir. So as per this result, I have evaluated that out of these 4 models, ResNet model has ResNet encoder has provided the better BLEU scores. You can see all the 4 different BLEU scores, BLEU 1, 2, 3, 4 in these values. Like these are the values obtained from VGG 16, then 19, Inception V3, and ResNet. So I have found that ResNet has provided the better BLEU scores when it is when image captioning model is built using GRU as encoder. And basically this is my conclusion only, that in this paper image captioning has been implemented using different encoders like VGG 16, 19, Inception V3, ResNet. GRU I have taken as a common decoder for all the models. Flickr 8 is the data set on which these models have been implemented, and the final evaluation has been calculated using the BLEU score, BLEU 1 to 4. And my result is that ResNet model, ResNet, when we use ResNet as encoder and GRU as a decoder, that it provides the best result among all the models. This is my evaluation actually, and these are I mentioned only few of the references. Thank you.
Okay, thank you, Gaurav. Just you have done here one comparison study, right? Using different
yes, sir,
deep neural network.
Yes,
so
sir, yes, sir.
Can you tell me what? Yeah, exactly. You can understand very well. So can you tell me exactly why actually this deep learning is used? Why? In which situation? Yeah.
Yes, sir. So deep learning basically it's based on the neural network, and as we know, the field of neural network is used to generate models so that it can work like a human being. There are various applications of deep learning, like in case of image processing or audio, video. So we want to generate some models that can work like a human. So this is the real you can say the use of deep learning field.
No, how? I could understand. That's a general actually answer. How it can means in what situation? How it can create like a human being? A different kind of.
So, sir, first of yes, sir. So first of all, we need some data set for that. Like suppose what kind of applications we want to develop. For we need to train the model. We will train the model by using the input and the output. There are obviously we have supervised or unsupervised
model. Yeah, listen, Gaurav, possibly you could not understand my point, right? Because there are different kind of classifiers, different kind of machine learning models. But in case of image processing and say language processing, we use a deep neural network. What's the philosophy behind that? Yes. Why we are looking? Why we are going to solve this kind of problem using a deep neural network? That's my question actually. Why?
Sir, we can say it is as of now, it is the last part of machine learning. Like we have various algorithms.
Not like that, right? When the feature space is not clear, actually, in that cases, actually, we use. That's fine. Okay.
Yes, sir.
You tell me one thing more, right? Did you
Actually
share-
uses
Yeah. Yes.
sir, it works on the concepts of features.
If the feature is not clear, space is not clear, right? So one
Yes,
thing
sir.
more. You use a ReLU activation function here. Which activation
Sorry,
function you
sir.
have
Please
used?
repeat.
Which activation
Which
function?
activation function?
Yeah.
Yes, sir. I have used softmax activation function, sir.
That's a softmax activation functions. Where in the out layer, in the out means output layer, or say hidden layer. Which kind of activation function you have used?
Sir, in image in image captioning there are two different parts, like in encoding and in decoding. So activation function has been used in the both of them.
No, yeah.
Activation function has been used while doing.
Yeah, listen. Softmax you have used in the output layer, I think, in the decoder part, perhaps.
Right, sir.
So in the VGG kind of thing, this encoder type, which kind of activation function you have used?
Sir, actually, I can check the code. Actually, there are many activation like 10H activation functions.
No, yeah. Listen,
and,
I'm just asking because there is some kind of rationality. That's why I'm asking. I want to know whether really do you know the actual the mechanism or not. That's what I'm asking. So did
yes,
you
sir.
use
Actually, you.
Yeah. Can you get one more questions? Why we use this activation function in deep learning?
Yes, sir. So use of the activation function is to represent a single value, like whether the resultant part is active or not. So result will be either 1 or 0, or it may be between 1 and 0. So to get a single value result from a vector, or you can say two-dimensional vector, to get a single value. So that's why activation function is used, so that we can get the resultant from that particular area, or you can say there is a resultant data. We can get a single value, and on the basis of that single value, we can identify what the actual data is, or what the actual result is actually.
Okay, fine. Okay, time is up, I think. Other panel members.
Thank you, sir.
Okay, Gaurav.
Yes, sir.
Gaurav, am I audible?
Yes, sir.
I
Yes,
have
sir.
one
Yes,
question. Just curious to know that have you opted the VG19 or 16 directly, or some modification done that at your end?
no, sir. Actually, in this paper, I have directly used only transfer learning. Nothing else. I have simply
So it's mean
used
that all these
VGGS.
are the existing approaches. All
Yes,
all
sir.
these
These
are
are
the
the
existing
existing.
approaches, and
These are the yes, sir. These
you
are the
have
existing encoders.
given this value 1, value 2, value 3, value 4. I have observed that if value 1 is giving better result, then what is the need of 3 to 4 instead of monogram? Why you are using biart or quadral?
Sir, actually, yes, you're right. But these are the parameters in evaluation metric. Like we have when we consider blue metric,
No, I mean
blue score.
the same.
So
It would be
these.
better if you use the different evaluation technique, measure metros. There
Yes,
are
sir.
other
Meteors.
technique as well. You
Yes, sir. I have studied.
variation. Okay. My question is relevant to the approach you have used. Why this ReLU? Why encoder, decoder, and all? I mean, deep learning stuff you are using. Why not AlexNet? This is only the temporal order you are or sequence to sequence you are going to read. This is the reason behind that, or you are just randomly someone used, I also used. What is the technical reason behind that?
Sir, actually, right now I'm working on a paper where I have used or I'm trying to use some attention-based mechanism. But as there are already existing some different encoders, so I wanted to find out which one of the existing encoders is the best encoder that may give me the better result. So, and I want to use the GRU as a decoder. So that's why I compared all these various
No, I get
combinations of
that. I
models
don't
like.
want to ask that question. That's fine. That's fine.
Yes,
I
sir.
mean, just I'm asking that why. I mean, this encoder decoder approach you use. Is there any temporal order is there? Yes. Okay.
Sir,
So
yes, sir.
so okay, I think even existing approaches you have opted, and okay, fine. Then what is the novelty in your approach? Novelty.
Sir,
Gaurav?
in this, yes, sir. Yeah, yes, sir. I will listen. Sir, definitely. Actually, I have found out the best combination of the existing models. This is my empirical study of the existing models, and what I have got it that.
No, if it's instead of 4, if you are picking fifth and sixth model, then it's also generates some outcome, definitely.
Yes, sir.
Okay.
Sir, I will definitely use some attention-based mechanism and will come up with a better model, sir.
It would be better if you make some modification and then propose your own. I mean, make some sense. Thank you.
Definitely, sir. Thank you.
Please, I have a question.
Yes, sir.
All right. Thank you very much. That was a scholarly presentation. However, I want to ask, using GRU as an encoder for getting the capture
as a decoder.
image, what? Yes, as an encoder or as a decoder, right? Now, what is the principle of operation upon which GRU is based on?
Actually, yeah.
Do you get my question?
Yes. What is the use of GRU? Like, you are asking what is the use of GRU?
I'm asking of the principle of operation upon which GRU is based on.
Yeah. Actually, it is a recurrent neural network, and it uses two different gates: reset gate and update gate. Gate are nothing but these are the memory cells that retain some information, and these two different gates are used. One of the gate is used to maintain the information that which of the following vectors or features will be used in the future, and which of the following features or vectors may be ignored for the next word generation. So it works on this principle to uses and that it uses two different gates, reset, and before this there was LSTM, long short-term memory. Obviously many of the models are using LSTM as a decoder, but I found this one is better because it uses only two different gates, and in LSTM there are three different gates, and it is newer version of recurrent neural network. So the simple principle is that it uses different gates to retain the information and to ignore the information. And there are its architecture is on different places there are different gates, and it receives information, and some forget part to forget the information and to retain the information.
Thank you.
Okay, next presentation.
Yes.
Okay. Paper ID 303, Mr. Jay Thakkar. Hello. Mr. Gaurav, you can please stop presenting.
Okay, thank you, sir.
Hello, am I audible?
Yes, you're audible. Please present.
Good afternoon, everyone. Is the screen visible?
Yes, it is visible. You can start.
So I am Jay Thakkar. Today I'll be giving a presentation on self-supervised learning for medical image restoration. My co-authors are Dr. Jignesh Bhatt and Professor Sarath Kumar Paradra from IIIT Vadodara. So today I'll be discussing these things. First of all, the background. Image restoration, as you all know, is the process of removing linear or non-linear degradation caused by different, let's say, blur, haze, or patient movements, etc., and noise in order to recover the clean, non-degraded version of given image. So for that, we are trying different self-supervised learning techniques to basically restore the medical images. So what is self-supervised learning? It is a kind of a new approach which combines supervised learning and unsupervised learning, you can say. So as you know, in supervised learning, there are basically two parts. One is pre-training, where you train, let's say, data of ImageNet, and the second part is fine-tuning on your specific task. So here, instead of the first pre-training part in self-supervised learning, it is called pretext pass. So instead of using labeled data like ImageNet, which is very hard to label and find, especially in the case of medical images, we are trying to use it like unsupervised learning, where the model does not require the label data, but instead uses unlabeled data. And the second part is similar to supervised learning part, where we have to fine tune us on a small level data set basically. So this is the problem description. Given a degraded MRI or CT image, which we are considering this task, the objective is to recover clean, non-degraded version of images. Here, assumption is that MRI images are corrupted by Gaussian or Gaussian noise, and CT images are corrupted by Gaussian and Gaussian noise. And the approach we are taking, as I said, is self-supervised learning. So the motivation basically is like in normal supervised approaches, we require a significant amount of ground truth examples, in any case like classification or segmentation or even in restoration. And it is a scarcity of labeled medical image data because it is a very specific field and we need professional labelers to who has information about the background of medical field to label the images. Other than that, the currently state-of-the-art self-supervised learning methods focus on problems like classification, segmentation, etc. And basically, we are trying to explore self-supervised learning for medical image restoration. So this is a kind of a basic architecture where we have this original image. We are degrading by Gaussian or some other, and we are including noise. So this is the image we are giving to model. Model is kind of like encoder decoder architecture. The first part is a pretext to it, which here we are experimented with. So we have taken two already trained models. One of them is called ROTNet, and another one rotation learning model method, and another one is called model genesis, which I will explain in detail. And the decoder is we are trying to regenerate or restore basically the image, which is hopefully noiseless and the degradations are reversed. So as I mentioned, self-supervised learning is suggested to address the issue where little or no label data is available. Data labeling is automated, which how it is automated, I'll explain it in a little bit. And the models run by leveraging the parts of unlabeled data basically. Benefit of supervised self-supervised learning is it does not require manual labeling like supervised learning. It is not limited to clustering and dimensionality reduction problem like unsupervised learning. And it is commonly known that supervised learning after a certain amount of epochs it doesn't affect the accuracy that much. So that can be solved here by using self-supervised learning. There are two major challenges that the self-supervised learning, it requires a lot of processing power, mostly because the choice of the pretest task is significantly impacts the result. I'll explain about that also in a little bit. So first pretest task is rotation learning. So imagine the normal supervised learning where you have imagined a data set. Your input is images and output is the label of those images basically in supervised training. So instead what we the paper in rotation learning done here is they took imaginary data set, but instead of labels like for input they are giving different rotated version of reference image itself of imaginary data set, and the output is the probability vector to predict the degree of rotation. So they rotated the input images on 0, 90, 180 and 270 degrees, and the network will try to predict whatever the degrees rotated at, and by that geometric transformation it will try to learn the features of encoded network basically.
Sir, excuse me, can you please speed up? It is already 10 minutes.
Yeah, sure. Similarly, the second approach is model genesis. So the rotation learning is trained on imaginary data set, which is in general data set. The model genesis is trained on specifically different type of medical data set like CT, X-ray, etc. And transformation applied are local shuffling, nonlinear, in-painting, out-painting, and the combinations of that basically. And for this, it is used 3D unit architecture with skip connection. These are the basic data set we have used For MRI, we have used brain tumor segmentation, and for CT, we have used Luna dataset. This is the machine specification. We have used 4 loss function and combinations of them to experiment and get the better result, basically, which is RMSE, SSIM, L1, and for testing, we have used PSMR. So these are some of the results. These are the MRI images. A is the original image, B is the restored image, C to H are the restored image by RotNet, and I to N are restored image by normal supervised function or ways, you can see, to compare basically like how different self-supervised from supervised learning, basically. And this is the restoration by CT. Here A is the given image, B is the degraded version, and C is the restored image by the model genesis approach. So this is the result based on the RotNet gives like PSNR. It's not that good, but like it was an experiment. Model genesis gives better result compared to the state of the art version, you can say, deep image pair. We also do applied ablation studies to get better understanding of how different parts of encoder and decoder or pretext or downstream task works, basically. And these are some of the results of that. So in conclusion, our method shows that equipped with different self-supervised learning strategies for medical image restoration, unlike existing approaches, self-supervised learning helps neural network to learn useful semantics without any explicit images. The experiment conducted on Luna and RAPS, and future work, we are planning to build more interpretable neural models based on self-supervised learning. And we can conduct experiments to solve different downstream tasks like super resolution and segmentation. These are my references. Thank you.
Okay, thank you, Joy. Joy, can you go to slide number 6?
Yes, sure. Yes.
So in the proposed model, see here, just you have added noise here.
Yes.
Can you justify what's the reason for this noise?
Sorry, what's the?
What is the justifications to include this noise? You have included.
Yeah, so it is normally found that in MRI, as I mentioned, that Raysian noise is commonly found, and in CT, Poisson noise is in general. While like let's say by machine, some noise is there in the existing image itself. So we are considering those type of noise, basically.
So this noise is added here. You have given plus symbol. Hello?
Yes, hello.
So why did you add the noise here? Did you get my questions or not?
Like why this specific noise or noise in general?
Noise in general, right? Any noise, because you have added here one noise, right? Plus symbol is there.
Okay, so.
Okay, then thank you, fine.
Okay, I'm not actually getting this. Sorry.
That's neural network regularization, right? Regularization, that's a research topic.
Yeah.
Network. Okay, thank you from my side.
Thank you.
Any questions from other chain members?
No, proceed.
Okay, sir.
Thank you.
So next presentation, paper ID 319, Mrs. Kamalaveni.
Hello, sir. I'm Kamalaveni.
Yes, ma'am, you're audible. Please present your PPT.
I'm Kamalaveni. I'm a research scholar at Amrita School of Engineering, Coimbatore, and I'm doing research under the guidance.
Excuse me, your PPT is not visible, but can you please share your screen? Yes, ma'am. Please do slideshow. F5, you can press F5, ma'am.
F5. F5 is not working, sir.
Okay, ma'am, please continue.
Or on the top, I think you can try this last one. On the top tabs, you can see like save and those tabs. So rightmost, you can try.
Slideshow is there from the third option from the right hand side in the previous slide. Third option from the right side.
Third option.
From the right, ma'am.
This is left. You have to go to right. You can see view, review, then slideshow is there.
Please go
You
to
may go
insert design, transitions, animations. After that, slideshow, design. Please go to next.
Next.
Design, transitions.
Next.
Other one that minimize this thing is stopping.
No, you're correct only. After design, you please move to the right. Please take the mouse cursor to the right hand side. Transitions are there after design.
Yes, is it?
Sir, if the
I think
if it is okay, then we can start with this one only.
Oh.
Like if the text
please
is visible.
proceed. It is fine.
Yes,
As well,
yes,
fine.
yes.
Please.
Ma'am. Yes, ma'am, you can continue.
My topic is first. Let me introduce me. I am Kamalaveni. I am doing research at Amata School of Engineering, Coimbatore. I have done research work under the guidance of Dr. Veni ma'am and Dr. Narayan Kudisa. The paper title is Adaptive Total Variation Based Image Regularization Using Structure Tensor for Residue Noise Removal in Brain Magnetic Resonance Images. These are the contents. Am I audible, sir? Are you able to hear me, sir?
Yes,
ma'am. Please continue.
Yeah, please continue.
These are the contents I will be presenting: literature review, problem description, and methodology and results and discussion. And let me say what is total variation regularization actually means. In image processing, total variation filtering or denoising both are known as regularization. And this is a method used to remove noise present in the images. And this method is actually based on the fact that images with maximum erroneous details have maximum total variation. So total variation is actually the sum of the image gradients computed at every pixel location across the entire image domain. That is integral of absolute image gradient across the image domain. By reducing the total variation of an image subject to the condition that denoised image must be close to the original noisy image, this will remove unwanted noise present in the image while preserving important details such as edges. And this concept was first pioneered by Rodin Osher-Patami in year 1992. And two commonly used variational models are TV-RF model and Tikhonov model. TV-RF model can remove noise properly and produce sharper edges, but it introduces staircase effect in the flat inner region. An image is composed of edges and flat regions. And other model, Tikhonov model, can eliminate staircase effect and but it blurs the edges. It does more smoothing. These are the two models, and they are described by a functional like this. The first model, TV-RF model, it uses a functional. The first term is called regularizing term. The first term is actually uses square of the, that is, it uses simply the gradient of an image. The second model, Tikhonov model, uses square of the gradient as regularizing term. These are the difference between two. These total variation regularization model compared to linear filters, median filters, it is actually enables efficient edge preserving denoising. Whereas linear filters, they can reduce noise, but they smooth away the edges to a greater extent. But the RF models is actually efficient in retaining edges, but there are certain drawbacks associated with RF model. There are loss of contrast, texture, and then loss of geometry. These are the other other drawbacks associated with RF model. Followed by RF model, different researchers, they have proposed adaptive total variation models to overcome drawbacks in the RF model. So next, I'll present existing adaptive total variation models. The first model is Chambol and Lyons model. It is a variable exponent based total variation model. The variable exponent based regularizing term it uses. This is it. The first term is del U square, that is square of gradient is used. So all those image gradients which are less than epsilon are considered as corresponding to inner region, and they are regularized using Ticknow model, and all those gradients which are above epsilon are considered as corresponding to edges, and the edges are preserved, regularized using TVRF model. This is how this model behaves. The second model, Eric model, it again uses variable exponent based total variation, a variable exponent based regularizing term. The variable exponent is a polynomial. It is P of del U. So wherever the gradient is actually greater than or less than or equal to M, the variable exponent is actually used as this polynomial. If gradient is greater than M, it is set to 0. This is how this model behaves. Next model is Chen variable exponent based model. Here again it uses variable exponent based regularizing term. The variable exponent here is alpha del U, which is 1 plus 1 plus del U by k the whole square. Here the second term is actually 0 at the edges. So the model will behave like an TVRF model. And the second term is 1 in the flat inner region. So it will be set to value, the exponent will set to value 2. So the model will behave like a Ticknow regularization model. So more smoothing takes place in the noisy inner region. This is how this model behaves. Next, Chiang-Chen model, which uses difference of curvature based adaptive model. Here variable exponent is actually P of D. It depends on difference of curvature. Difference of curvature is actually difference between UNN and UEE. UNN is actually directional second derivative of image computed along gradient direction, and UEE is directional second derivative of image computed along edge direction. At the edges, both UNN and UE are large and they're actually almost same. So the difference is 0. So 0 by D max is actually 0. So the exponent actually becomes 2. That is in the inner region. So sorry, in the edges, the DNN is actually max. So difference is actually max, and UNN is max, UE is actually small. So the difference is a large value. So D by D max is actually becomes 1. So the square root of D bar is actually now becomes 1. So the exponent becomes 1, constant 1. So the model behaves like an RF model. In the inner region, that is isolated noise wherever is present, there both the terms are large and are almost equal. In that case, its value becomes 0. So when it's 0, the exponent becomes 2. So the model behaves like a Ticknow regularization model. More smoothing takes place and the noise is removed. This is how this model behaves. These are the few existing popular adaptive total variation models. And let me explain what is the problem I have chosen. Though these adaptive total variation models able to preserve edges, but it may change important information which is present in the images. That is, fine details, texture, contrast may be lost. The reason for information loss is there is an error in distinguishing between edges and the flat inner region. So most of the adaptive total variation models, gradient-based edge stopping function is used as a tool to determine edges. And we have proved in our previous work, that is in the previous work, it is proved that in locating edges, edge function which is based on trace of structure tensor matrix is more accurate than edge stopping function based on the simply gradient vector. So this gives new direction in the research work, that is to develop an adaptive total variation model using trace of structure tensor based edge stopping function, which more accurately locates all the edges, including weak edges, thin lines, and it distinguishes edges from the flat inner region. This new adaptive model totally it stops diffusion across the edges and it permits strong diffusion in the inner region. And this proposed adaptive total variation model, with making use of structured tensor matrix, it efficiently removes residual noise present in the brain magnetic resonance images, and also it eliminates drawbacks associated with conventional adaptive total variation regularization. Next, let me explain the proposed model. The proposed adaptive total variation model, it actually makes use of the structured tensor matrix, which is used as a tool to determine where all edges present. So I'm explaining first what is structured tensor matrix. It is actually 2x matrix, 2x2 matrix. It is a product of del U into del U transport. Here del U is actually gradient of image. It's a column vector consisting of Ux and Uy. Ux is derivative of image along x direction. Uy is derivative of image computed along the y direction. So here again the structured tensor matrix is used as a tool to determine where edge is present. Here in determining whether a pixel is exactly correspond to an edge or inner region, to take that decision, the structured tensor matrix considers pixels which are in the neighborhood. So for which what each of the element wise smoothing using Gaussian filter with standard deviation rule is to be done, because it considers neighborhood pixels to determine whether a pixel is part of an edge or inner region. Next, how to this structured tensor matrix helps in determining where the edge is present. So in order to find out edge direction exactly, this tensor matrix, 2x2 matrix, you have to apply eigenvalue decomposition. When you do eigenvalue decomposition, you get eigenvalues L1 and L2 as per this equation, and you will get eigenvectors E1 and E2 as per the equation, that is 1 and 2. These two eigenvector E1, it is consisting of two components, E1x, x and y components. E2 again consisting of two components. These two eigenvectors are actually orthogonal vectors. So their dot product is equal to 0. And eigenvector which is corresponding to maximum eigenvalue is taken as gradient direction, which represents direction along which maximum gradient variation is there. And eigenvector which is corresponding to
Excuse me, can you please conclude in 2 minutes? It has already been 10 minutes.
Okay. And h it corresponds to smallest eigenvalues, actually h direction, which is more accurately you could determine edge and gradient directions like this. And these are merits is actually it is element by element smoothing that actually and cancellation effect of negative gradients both are actually avoided. So it the error in locating edges is minimized, and using eigenvalues L1 and L2 you could accurately determine whether a pixel is part of an edge or inner region or it is a corner. That is, you could compare the values like this, L1 whether it is equal to L2, whether it is approximately equal to 0, and if so it is part of an edge, and if it is L1 is greater than part of an inner region, like you could decide correctly by taking comparing the L1 and L2, you could decide correctly where the pixel part of an edge or inner region. And edge function which is based on trace of tensor matrix, it behaves like this, which is defined like this: e power minus h by a the whole square. H is trace of tensor matrix, which is sum of L1 and L2 eigenvalues, and A is gradient threshold parameter. So wherever edges are present, there the sum H1 plus H2, that L1 plus L2, H value will be high. So there this exponent function will have 0 value. So diffusion is totally stopped at the edges. And wherever inner region, there the L1, L2 values are nearly 0, almost equal to 0. So the exponent becomes 1. So the diffusion is full diffusion is allowed in the inner region. This is how edge function based on trace of structured tensor matrix behaves. And now the adaptive total variation model making use of structured tensor matrix is proposed like this. This equation which is describes the proposed model. Variable exponent based regularizing term is used. The variable exponent is alpha h, which is 1 plus c of h, and weight of the fidelity term is beta h, which is again it is adaptively selected, which is set to 0.2 into 1 minus c of h, and c of h is at edges it is 0. So the model behaves like an RF model. In the inner region, C of H is 1, so the exponent becomes 2, so the model behaves like a Techno model. And exponent, this adaptive fidelity term, its weight is actually set to low value in the inner region and set to high value at the edges. This is how the model behaves. And the model, how it behaves, how the algorithm is expected, how it works is at every pixel position, the structure tensor matrix is computed and eigenvalue decomposition is applied, and L1, L2 eigenvalues, eigenvectors E1, E2 are determined, and then trace of tensor matrix is found, then edge stopping function is determined, and then value of edge stopping function, is it 0 or 1? That condition checking takes place. If it is 1, means that a particular pixel is corresponding to inner region. So the regularizing term is set to square of the gradient, and regularizing parameter beta of H is set to much smaller value compared to 0.2, and the model behaves like a Techno model and more smoothing takes place. If the pixel is actually corresponds to an edge, then C of H is actually 0. The pixel actually corresponds to an edge. Then the regularizing term is set to total variation of the image. That is simply absolute gradient of an image is used as regularizing term, and the parameter regularization parameter set to 0.2, and the model will behave like an RF model, and this enables efficient image, efficient edge preservation. And the proposed
whether the time is up or not. Hello, how much?
Just 2 minutes, I will complete it. Proposed energy functional describing adaptive total variation model need to be solved. That is, equivalent PDE need to be determined. Applying steepest descent method, the PDE is found, and this PDE is actually for which orthogonal decomposition is applied, and orthogonal equations are orthogonal decomposition is done, and that describes diffusion along gradient direction how much, diffusion along edge direction how much. This first term describes diffusion along gradient direction, second term describes amount of diffusion along the edge direction. So in this PDE, the direction second derivative along edge direction, along gradient direction, both need to be now replaced by directional second derivative, which is along edge eigenvector E1 and eigenvector E2. That is, UNN need to be replaced with directional second derivative of image computed along E1 eigenvector. That is this UWW. And replace UEE by UVV, that is directional second derivative of image computed along the edge direction. So now that replacement need to be done in the orthogonal decomposition PDE, which is equivalent to the energy functional describing the proposed adaptive TEV model. And this final partial differential equation we got, and this is actually equivalent to the proposed energy functional, and it can be solved using numerical iterative algorithm. This numerical iterative algorithm is the first equation describes that Uij n plus 1 is.
Ma'am, excuse me, can you please conclude, ma'am?
Okay, and the results are denoised using all the methods, and then quality metrics SSIM, PSNR, FSIM, and mean average error are computed, and the values are tabulated, and the proposed method produces higher value of SSIM. That means highly similar method, which is similar to denoised image, the highly similar to original image it generates, and PSNR value also larger compared to other existing methods. That means this algorithm outperforms the other methods. And it proposed algorithm generate visually enhanced image that is proved from the higher values of FSIM. And other quality metric, mean average error is minimum. That means minimum distortion is in the reproduced image. It enables the efficient edge preservation. These are the visual quality of images produced by different algorithms. And finally conclude, this efficiently removes the residue noise present in brain magnetic resonance images, and it is actually outperforms other existing models both quantitatively and qualitatively. Hello, sir. Thank you, sir.
Any
Hello.
questions from session chairs?
Thank you, the organizers, for giving me opportunity to present this work.
Yeah, I have one question that somewhere mentioned L1 and L2. Are these the LEGO and ridge regularization or something else from the equation you have extracted?
L1, L2 are eigenvalues of the structure tensor matrix.
Type of, okay, this is something different. Okay. Okay.
It's a eigenvalues of the structure tensor matrix, using which we could find out whether a pixel corresponds to an edge or inner region or a corner.
No, fine. Thank you.
By comparing their values and checking for the conditions like is L1 equal to L2, it's equal to 0.
It's okay. Thank you.
Thank you.
Thank you, sir. Thank you all for giving me opportunity to present.
The next presentation, paper ID 362, Mr. Himanshu Sharma.
Yeah, hello. Am I visible? Am I audible?
Yes, you're audible.
Sir, I'm not able
Mrs.
to
Yes.
share my screen.
Mrs. Kamalaveni, can you please stop sharing the screen? Mrs. Kamalaveni. Ma'am, Mrs. Kamalaveni, are you available? Okay, Mr. Himanshu, you can start sharing.
Yeah, thank you. So is the screen visible?
Screen is visible. Yes. Please present the slideshow.
All right.
Yes.
So
you
good
can
afternoon, everyone. My name is Himanshu Sharma, and I am doing my PhD in Central University of Jammu. And the title of my manuscript is A Survey on Attention-Based Image Caption, the Taxonomy, Challenges, and Future Perspectives. And this is the outline of my presentation. Okay. So we see that humans have an outstanding ability of looking at the image and interpreting its content. For example, we see in this figure 1, and we analyze that this little girl is playing with paints, and there are some backgrounds, and she's sitting on the grass-like stuff. So the image captioning is actually a mimicking of this human ability by a computer. So we say that image captioning is actually generating a description for an image by the computers. As we see in the figure 1, these descriptions are generated by the computer, and they are like the human generated descriptions, and they describe the contents of the images quite efficiently. So mathematically, we say that image captioning is actually a mapping of image with some other modalities that consist of natural languages like the meaningful phrases, the semantic sentences, and so on. And also the generated captions should be short enough that they should conclude in 1 or 2 sentences, and also should describe all the salient contents of the image. Okay, so as we already saw in one presentation, that image captioning architecture consists of 2 subcomponents, namely the visual component and the language generation component. The visual component consists of visual detectors, the global and local feature extractors, and all this information is extracted and then presented into to the language generation model in the form of a context vector. The context vector is then processed by the language generation component and is generated, and it generates the descriptions for the given image. So earlier, when the image captioning was just started, these visual detectors and language models were machine learning based, but then with the introduction of more efficient deep learning based models like CNN and RNN, we introduce these models into our existing architecture, and then this existing architecture was transformed into a novel architecture of encoder and decoder structure. So we see that image captioning has a number of application fields nowadays, like these visual assistance, multimodal search, machine learning, securities, and these remote sensing and machine medicine captioning has been the novel or the recently introduced applications of captioning. Okay, so as we already saw that the encoder-decoder architecture consists of certain restrictions or limitations that cannot conclude the image perfectly. And as we see that humans have an ability to focus only on the salient contents of the image and neglect the rest. For example, from this image, we can conclude that a cycler is cycling, and we automatically don't focus on other stuffs like the mountain, the sky. So to introduce this kind of mechanism into the computers, we invented the attention mechanism within the image captioning architecture. So having an attention mechanism give image captioning models an ability to focus only on the salient contents of the image. So we see that we have an attention mechanism, and this attention mechanism now generates a dynamic context that tells language decoder to focus only on the salient content and ignore the rest. So we reviewed the literature of almost 7 years, starting from 2015 to up to now, and concluded that there was no proper image captioning review on attention. So that's why we undertake this comprehensive review. And on the basis of all the models we studied, we classify attention with respect to image captioning into these following 5 important types. They are the regional attention, the semantic attention, the spatial attention, the emotional attention, and the hybrid attention. So the first one and the most basic attention is the regional attention. In regional attention, an input image is divided into an equal number of areas, and then at any time frame, these regions guide the attention mechanism to focus only on the salient content. The regional attention is further of 2 types, namely hard attention and soft attention, depending on whether 2 or more image regions can be focused or attended concurrently. In figure A here, 6A, we can see that only one of the image region is currently active in one time frame, and this type of attention is called as hard attention. And then in this figure, we see that more than one image regions are active, and this type of attention is called as soft attention. And these are the pictures we studied. And just as we saw Blue Force score being the most dominant evaluation matrices, and these are the performances of the region-based attention model. The next is the semantic attention, and semantic attention is an upgrade of existing regional attention. In semantic attention, the regions can be non-uniform, and the regions only consist of the semantic details. For example, here we see that there are a lot of background in this image, but when it comes to the image region, we have only the regions that consist of the semantic details. So this type of model makes the blue score or the performance of image captioning more efficient. And these are the models that we studied in terms of semantic attention in the literature. So we see that a lot of work being done in the semantic attention. And also the performance is better than the regional attention. The next one is the spatial attention. So spatial attention tries to decode the relation between the semantic visual contents that appear in the image. We see that there are many circumstances where 2 or more visual images or objects can be related to each other, and this information needs to be described in the description. So spatial attention focuses on this task, and it generates the results or the description that consists of the relationship between the semantic objects. And these are the spatial attention based model. And we see that the performance using the spatial attention has improved further in the literature. The next is the emotional based attention. As we see that a human can generate a number of captions for a given image. For example, we can generate some romantic captions. We can conclude it in humorous form or in serious form. So to enable or implement this type of captioning, the emotional based attention model was implemented. And within the literature of our 7 years, we just found this one model that was implemented using the emotional based attention. And this is the architecture of this model. And then the last is the hybrid attention. And recently in late years, the researchers concluded that using or implementing only one kind of attention is not enough. So the hybrid attention concept is to combine the existing 2 or more types of attention and then generate better results. So these are the models hybrid attention-based model, and the current state of our performance of image captioning model using attention-based mechanisms is achieved using this hybrid attention model, as we can see here, 40.7 blue force score. And these are the benchmark data sets for image captioning training and validation. And out of these data sets, this MS-COCO data set is the most widely used, and most of the works are being done on this one. So after reviewing this whole literature and concluding after 50+ research papers of attention-based image captioning, we found the following research challenges. The first one being the limited accuracy and efficiency in the real-time situation. The scarcity of domain-specific data sets. For example, the novel application areas of image captioning, like the remote sensing and medical captioning, still don't have the proper or the efficient data sets for better performance of image captioning. Then we have the inefficiency while generating the extended sentences. The attention misinterpretation is one of the prime challenges in image captioning nowadays. And then we have the limited use of modern deep learning techniques like the transformer and the graph convolutional networks. So there are only 2 or 3 models that implement these kinds of architectures now. So this work can be extended in terms of developing real-time image captioning systems for visual assistants, the non-English image caption generation systems, where the captions can be such as regional languages, like we have the Punjabi, or we can use other languages like Hindi and so on. And our work of PhD is also on this non-English image caption generation system. Then we have the personalized IC system, such as the one used in Facebook and Instagram, where we identify the images of the people, and then we try to like tag them or describe them what they are doing. Then we have the visual captioning system. This is an extension of the image captioning system, where we generate the captions for the videos. And then we have this visual question answering system, where once an image is input to a visual question answering model, the model tries to answer the queries related to the image. And these are the reference of the model, attention-based model that we studied in our survey. So that's all from my side.
Yeah, thank you.
Any questions? Yeah.
So any questions from session chairs or participants?
Thank you. No questions from my side.
Okay, sir.
Okay, sir. Thank you.
Yeah, no question from myself.
No question my side.
Okay, sir. That was the last presentation of the session. On behalf of NIT Raipur and organizing committee of the conference, I thank you all for sparing valuable time as well as providing valuable insight to the others. So all the session chairs are kindly requested to fill the evaluation sheet so that the best paper award can be decided and finalized. So all the Google form links for all these evaluation sheets have been already sent to the corresponding session chair email IDs yesterday evening.
So thank you. Already I have done. Thank you, everybody. Thank you, Dr. Sonal. Thank you, Dr. Kishan. Thank you, Dr. Surendra Verma. I'm really happy to work with you. Thank you. Thank you, everybody, from my side.
Yes, sir. Thank you very much, sir.
Thank you.
Thank you, Dr. Saru.
Thank you, NIT Raipur, organizer, convener, and coordinator, as well as the colleague, the session chair, all the valuable participant and audience. Thank you very much.
Thank you, sir.
Thank you, sir.
Okay.
Thank you, sir.
So, Sal, may I leave now? It is over, I think.
Sure.
Yes, sir. Sure,
Sure.
sir.
Thank you. Thank you, Krishna, sir.
Okay.
And thank you, Dr. Alok Kumar, sir, as well. Thank you all.